All right, so we just came up with these equations. And as we said, there were 4 equations of motion, 4 state variables, so all seems good. But we asked the question, what's going on here? Why is this any different from the CAT problem? And actually, there's something really important that is different about this problem, why we chose this problem, even though it has a lot of the same properties of the CAT problem. I mean, one reason is that it's just another, one to work through that has a lot of the same issues. But the key issue here is that this problem is one where the answer is heavily dependent on this value of rho, right? And in particular, rho is not something that's constant, right? In the CAT problem, the cat's jumping out of a building. We're assuming the atmospheric density at the top of the building is kind of the same as it is at the bottom of the building. So you really don't have to have a very complicated model for atmospheric density. You just say it's 1.2 kilograms per meter cubed. In this case, it matters enormously that that atmospheric density varies. And so in order to actually make further traction, the next step we would really need to do is develop some kind of model for this rho. So let's talk a little bit about how you might go about doing that. So before, Alex told us that we could sort of think about what the density of the atmosphere was as a function of altitude, or R sub y, and she observed that at the edge of the atmosphere, at 100 kilometers above the Earth's surface, right, we had about 5 times 10 to the minus 7 kilograms per meter squared, or per meter cubed. And at the surface of the Earth, it's about 1.2 times 10 to the 1, or 10 to the 0, sorry, 1.2 kilograms per meter cubed, right? And pretty clearly something is happening in between these two, right? So how are we going to deal with this? Well, one possibility is simply to say, look, for a first cut model, I'm going to assume it's linear, right? And that's not an unreasonable thing to do. It's not right. Like, I'll guarantee you, if you go and you start to look around on the interwebs, you will find that atmospheric density does not vary linearly with height. Yeah. But on the other hand, it's a whole lot better model than assuming it's constant, right? So as a first cut model, my inclination might be to say, okay, for sort of model version 0.0, right, I might say, okay, rho as a function of Ry, right, is equal to, well, the intercept is 1.2 kilograms per meter cubed, right? And my slope is 1.2 kilograms per meter cubed per 100 kilometers, right, times Ry, and it's equal to that for Ry less than 100, and it's equal to 0 for Ry greater than 100, right? Now that's not going to be a very good model, but it's an example of sort of looking at a very limited amount of data and saying, okay, what's a model that we could build, right? And obviously a next cut model might be to say, okay, I'm actually going to go online and I'm going to spend some time and find a sort of data set, right, that tells me what the atmospheric density is at a set of different heights. And then I would be able to either build a sort of model that has a linear interpolation between these, or there are a variety of other sort of fitting tools within MATLAB, so I could use sort of MATLAB magic to write a function that passed out the density, right, and that took as an input what the height was, right? And if you imagine how you might deal with this in a sort of MATLAB context, you would probably initially write that function using this simple model. And then as you iterated in your process, as you went to model 0.1 and 0.2 and 0.3, you would try to improve the quality of that model until you got to the point where it felt like you weren't doing any more, the benefits of improving the quality of the model were marginal. Right? And presumably after a couple of iterations of this, you're probably going to hit the point where those benefits are marginal. So that would be my inclination. I think this is one of the places people often get stuck with this type of work, is that you've got some fairly complicated system, like what the density of the atmosphere is, and it's like, how do I actually model that at all? Well, the answer often is you start somewhere and you start simple.
Right, because a lot of times actually you end up using lookup tables just to figure out if you're dealing with a system at 30,000 feet or 50 kilometers, what's going on. But one thing I want to mention too about modeling in terms of thinking about this density is when you start here, this clearly isn't what is happening. It's not linear decreasing, but you have to be able to explain to your audience why you assumed this, right? So just a very quick explanation of why something like this is more reasonable is you could say, well, the atmosphere has different zones where there's different characteristics of what's going on. So you might have pulled a density from each part of the atmosphere and said, okay, I've captured at least one, I've created this function, and it at least showcases the fact that the atmosphere is changing in these different, whether it's the troposphere or something, over time, all the way until it gets to space. So you want to have some sort of qualitative explanation of why this is an okay submodel, essentially, to use in your model.
Yeah. I mean, I think that the other thing I would say is that with regard to this type of really simple model, it's absolutely not right, but it is useful in the sense that it also is sufficiently simple that you can build it quickly and you can make sure that it actually does what you expect it to do quickly. Whereas if you tried to, say, build this more complicated atmospheric model initially, I bet you would end up spending a week trying to get it working, and you would never actually have any confidence that it was working. So starting simple is great and a really important thing to do, but also having a sort of trajectory forward with regard to making that simple model more complicated is also
right.
important.
And what's nice is in your code, you have the density input all set up on the main part of your code, and so switching these out becomes easy. So starting simple also is not something that's going to hurt your actual overall program.
Along these lines, a conversation that's come up a lot for me in Project 2 with students is, well, what happens if we get stuck here and we never make it to here? Think about what it would change in your output if you made the change from this to this, or from this to the next more complex thing. That's what we're interested in seeing at whatever your endpoint is have you thought about what the next thing might be? What kinds of changes would that make in your larger model? How important do you think that that is?
Mm-hmm. Is it important, thus, in this case, just that the density is decreasing, or does it become important that there's areas where it decreases slower than in others?
Yeah, exactly. It seems like we're at a good place to end this video. An obvious next step we might take would be to ask the question, okay, we've got a set of differential equations, what do we do next? So maybe we should spend a little bit of time talking about what those next steps might look like, but I don't think we're going to write any MATLAB code here.